Hello, welcome to the Past Marathon Linux edition. We're excited you could join us today for Anthony Nocentino's session on monitoring Linux performance for the SQL Server admin. The Past Marathon consists of 6 consecutive live webinars delivered by expert speakers from the Past community. The sessions will be recorded and posted online after the event. You will receive an email letting you know when the recordings are available. My name is Tracy Bajano. I will be the moderator today. I have a few introductory slides before I hand over the reins to Anthony Nocentino. Next slide, please.
Oh, that's me.
If you require technical assistance, please type your question into the question pane located on the right side of your screen and someone will assist you. This question pane is also where you may ask any questions throughout the presentation. Feel free to enter your questions at any time, and once we get to the Q&A portion of the session, I'll read your questions out loud to the speaker. You are able to zoom in on the presentation content by using the zoom button located on the top of the presentation window. Note that there will be a short evaluation at the end of the session. Your feedback is very valuable, so please take a moment to complete it. It will appear in your web browser at the end of the presentation. Next slide, please.
Coming at you.
Thank you to our presenting sponsor, SUSE, for continued support of our event. With their help, PASS is able to provide another exciting virtual conference. SUSE and Microsoft have been working together for over 10 years. Over the past year, they have closely collaborated with the SQL Server team at Microsoft to bring SQL Server 2017 to the SUSE Linux enterprise. Next slide, please. The PASS Career Center can connect you with your dream job opportunity. Utilize this resource to review posted careers, create applications, post anonymous resumes, and more. Connect with a worldwide network of employers and multiple enterprises by visiting pass.org/careers.asp.x. Next slide, please. This Past Marathon session is presented by Anthony Nocentino. Anthony is an enterprise architect, founder, and president of Centino Systems, prototype author, Microsoft Data Platform MVP, Linux expert, and a voracious student of the latest computer science technology. Anthony is also working towards a PhD focusing on high-performance, low-latency data access algorithms on solid-state disk and spatial data-based systems. Without further ado, here's Anthony Nocentino with Monitoring Linux Performance for the SQL Server Admin.
Cool. Thank you, Tracy. I appreciate the intro. And just to add to that a little bit, I have a blog. So a lot of today's content is on my blog already and is also in several of my Pluralsight courses. So if you guys want access to those courses for free, hit me up and I'll give you a 30-day trial. And the reason I'm telling you this isn't to sell you stuff, but because you'll have a much more deeper dive, expansive library of stuff to have access to, especially with these topics that we're going to go through today in the amount of time that we have. And do hit me up on Twitter or shoot me an email if you want access to that stuff. And so let's get into what we're going to get into today. First off, we're going to talk about the Linux system architecture. What are the core building blocks underneath the operating system itself? Then we're going to look briefly at the SQL and Linux architecture and look at how that bumps up against the Linux system architecture and how those things interact with each other. And then we're going to break down kind of the major components of any system, right? CPU, disk, and memory. And then we're going to look at the operating system abstractions for those things, processes, pages, and file systems. We're going to kind of go a little bit higher level than blocks when we talk about disks. And for each of those components, I'm going to talk about tools that you can use to poke and prod your system to get that perf data that you're interested in. In addition to that, when we get to the end, we're going to zoom out and look at system monitoring tools and some packages that are available to you to go and get that perf data that you need to troubleshoot your system. So the things that we're going to cover today, we're going to talk about the Linux operating system itself. We're going to talk about how it works. And I'm a firm believer in understanding how things work. And the reason is, and I get accused of teaching seminars a little bit too academically, but I really want you to understand what's going on behind the scenes, because if I tell you that and you guys get to the point where you really understand the internals, then you become a more general problem solver. If I just give you a script or tell you a value that's bad, you can solve that problem that you're working on. But what about the next one, right? And that's why I really want you to understand what's happening under the hood. We're going to talk a lot about tools to view perf data today, and we're going to talk a little bit about what's good and what's bad. Not particular values, but kind of scenarios on when things kind of fall off cliffs and start to look really bad. What we're not going to cover is a lot of SQL Server internals. We're not going to go into what's going on inside of SQL Server. We're going to focus on Linux and the operating system. And I'm not going to tell you how to troubleshoot anything, right? I'm giving you the tools to go build your own troubleshooting techniques and go through those motions. So let's get into the Linux system architecture. And it's an operating system, and it has one job. The job is to control access to the hardware, right? Those physical resources, those things that make up our computer, CPU, memory, and disk, right? Now, the thing that controls access, the piece of our operating system that controls access to those physical resources is the kernel, right? And its responsibility is resource management and access, right? It's the thing that doles out the resources and also controls access to who gets what and when. Now, the core way that it doles that information out or allocates it is with these operating system constructs: processes, pages, and file system, right? Processes are execution contexts, pages, memory, file systems, disks, right? Now, if we're sitting at our terminal executing programs, we're interacting with the shell, right? That's the thing that launches our programs. Our programs inside of their code execute system calls to ask for the resources that they need. Of course, they're going to do their work, but when they need something, like they need some memory, they need to schedule a new thread, they need to read a file from a disk, those system calls are going to execute in that program code. It's going to pass control over the system call interface into the kernel, and the kernel is going to go do that thing, right? It's going to allocate a process, allocate a page, or read or write a data file, right? And so that's how that works. Now, if I'm sitting at the shell, right, I'm a user, I interact with the shell interacts with the program interacts with the kernel via the system call interface, the kernel goes and interacts with the hardware, and that's kind of the pipeline of information going from top to bottom. Now, there's two terms I'm going to throw at you: kernel space and user space. What's happening here is when I'm a program and I'm running and I'm doing things for you, right? I'm doing the task, the computation, the sorting, the averaging, whatever it is inside my program, I'm in user space. But if I have to go read a file, allocate a page, or which is memory, or schedule a new thread, I'm in kernel space, right? I'm asking the system to do work for me. And we generally want to stay in user space, right? Because that's going to make it seem like our program state is moving forward to accomplish the task that needs to get done, right? We're not doing the work under the hood of allocating the resources, right? So we want to stay in user space as much as we can. I'm going to show you later how you can differentiate when your process is predominantly in user space or in kernel space. So we've probably seen this diagram a lot, right? This is the Linux SQL Server on Linux architecture. This is the process layout. We're going to focus on the bottom half today. We're going to look at the Linux host extensions and how they interact with the operating system. You can see that arrow right there. You see Linux OS calls, right? The Linux host extensions inside of SQL Server on Linux are the things that execute the system calls that ask the operating system to do work, right? And we know that that bounding process inside is Win32, which interacts with SQL. SQL interacts with the host extensions, and the host extensions ask the operating system to do the work, and then the operating system does the work. But I'm going to tell you something on how I think this whole system is viewed, is that SQL is virtualization. And I've studied virtualization academically for many years, and there's a class of virtualization called process virtualization, not machine virtualization. We're not emulating hardware, right? But what's going on inside of SQL is we're presenting another environment inside the process's execution context that's different than that of the underlying operating system, right? We're Win32 on the inside, which is a Win32 process, and we're Linux on the outside, right? So we have this concept where it's PE on the inside and ELF on the outside. And so that process virtualization kind of gives us some interesting things that we need to understand, right? But the first point I want to cover is that process virtualization, that container, not capital C, lowercase c, because I don't want to say container, is purpose-built for SQL Server, right? There's some serious engineering that's going on to make this thing rocket fast. So by no means are you going to sit here and go virtualization. That's a performance penalty. It's not. But what it is doing is emulating that environment. Now, for that, we need to understand that this is a hybrid environment. It is Win32 on the outside, or on the inside, and Linux on the outside. So we need to understand that, right? Because we need to understand resource allocation and management inside of SQL, right? How it does the things that it does. We also need to understand how that turns into Linux OS performance fundamentals, which is what we're going to march through as we get through this presentation today. And if you're an advanced performance tuner in the SQL Server world, you need to understand that the tools that you're used to using to debug SQL Server are different now, right? Because of the way that the program binary is laid out, right? You're used to using WinDBG to debug that Windows-based process? Well, there's a new tool set that you have to use to debug it on a Linux process, and the fact that it's Win32 on the inside and PE or ELF on the, excuse me, Linux on the outside, ELF. So let's move into the first stop in our system, CPU and the core operating system abstraction process. So what is a process? Well, a process is executing program, right? It's a thing that's up and running. It's the code or the binary, the memory or and the resources allocated to that memory, right? And it's that entire set of information. And that's really the running program state of the thing that we're trying to do. Inside of that, we can have threads or lightweight processes. You'll see that abbreviation very frequently. A thread has shared access to the resources in that process address space. So a process will always have one thread, but can also have more than one thread to increase the concurrency of the execution and also be able to access all of those resources in that memory space as a shared resource. I'm going to show you how it looks in terms of SQL Server in a few minutes. To understand how that works, we do need to understand how processes and threads are created. When a process is created, it's forked, right? That's the system call where we execute the fork system call. We make a copy of the process that we're working with, and then we link those two together in a parent-child relationship. We assign a new process ID to the child, and those two are permanently linked to each other in a parent-child relationship. If I need to load a new binary, right, to replace that child, I launch exec, and this is how a new process is started every time. Is I fork the process, I make a copy, same exact process, and then I exec and replace that executing or that program code with the new program that I want to execute. And so that's called a fork exec. In terms of SQL Server, we're going to see just a fork, and then we're going to see clones for threads. What a clone does will allocate threads that can share the same address space as the thread creator or the process, right? And those things are cheap and very fast. And so that's how we can add scalability to a system very quickly. So that parent-child relationship builds a process tree, right? And so that hierarchy is what's going to exist. And we need to understand from a process management standpoint, if we kill a parent process, all of its child processes die, right? And so we need to, from a process management, we need to make sure that we aren't doing things that we don't need to be doing to the parent that might cause issues further downstream for those child processes. So we're probably familiar with in SQL process states, right? Well, that concept exists in operating systems as well. And we're going to walk through the process states of Linux right now. So if I'm up and running, I'm on a CPU and I'm doing my work, I'm running, right? I'm happy, I'm getting things done. But I can transition from running to sleeping under a couple conditions, right? The first condition is I've exhausted my quantum, which is a concept SQLS is that's very familiar to folks that are familiar with SQLS. So I can exhaust my quantum, transition to sleeping, or if I'm a running process and I need I/O, then I'll transition to sleeping until my I/O is complete, or I get preempted, right? It's a significant difference from SQLS in that if I'm a process and I'm running, something more important than me can come along, or an interrupt can come along and bump me off of the CPU. So under those three conditions, I can transition from running to sleeping. Now let's say my I/O completed, or it was just a simple quantum exhaustion, or I got preempted and it's my turn to get back onto the CPU. What I'm going to do is I'm going to transition into a runnable state. And what that's going to do is going to put me in line to get access to the CPU again. It's a queue, literally a line to get access to the CPU. Now that queue is not processed sequentially. We're going to talk about that in a second. And the scheduler is going to come along and it's going to pick the process that it thinks needs to have access to the CPU next, and then puts that on the CPU. Now there are two other states that I want to cover today for you guys, and that's stopped, right? I'm basically a process that's stopping and deallocating my resources, and also zombie. I just like to bring up zombie because it sounds cool. No, what zombie is a process probably had a pretty severe error, probably a bug in the program code, and it crashed. It got unlinked from its parent, linked to the process ID 1, and will live until your system reboots, consuming the resources that it has. Generally, you're going to be in a zombie state because something really bad happened. I was doing some extreme memory pressure testing with SQL Server on Linux, and I put it into a defunct or zombie state a little bit ago because I was doing bad things to it, right? You don't want to be in the zombie state. Now, when we talk about process states, this has an influence on performance, right? Because if we're a running process, we're great. If we're sleeping and we're waiting on I/O, bad news, right? I'm going to show you how to identify that in a second. So we talked about the runnable queues, right? Who gets picked next? Well, let's talk about that, right? We're going to look at process and thread scheduling. The unit of execution, or unit of scheduling, I should say, is the thread, right? Not the actual process itself. So the execution context, the thing that gets thrown onto the CPU is the thread. There's several different schedulers in Linux, and a default scheduler is schedule_other, sometimes called schedule_normal. It's a time-sharing scheduler, which means it's preemptive, right? So I told you just a second ago that someone can come along and bump me off of the CPU. Why? Because someone could have a higher priority than me. And there's two different types of priority in Linux. There's dynamic priority and then priority based on niceness. So dynamic priority is calculated inside the scheduler, right? It's a value that it calculates based on the scheduling algorithm to pick who's next, right? And that's happening behind the scenes. And what it's really trying to do is be fair. It wants to make sure that bigger processes get bigger chunks of time without starving smaller processes that need to be interacted to get on and off the CPU very quickly. So that's what's happening with the dynamic priority inside of the kernel. We can assert our own priority on a process with a thing called niceness, right? We can lower the niceness or make it less nice by saying, I want this process to have a higher priority. Those values are taken into account, and that's how the scheduler picks the next process. We also don't have a fixed length quantum. That's another way that we can get bumped off of the CPU. There's a dynamically calculated quantum based on that internal priority and other parts of what's going on inside of the scheduler. And that can be a value in terms of milliseconds. And one of the tunable parameters given by the product team for SQL Server on Linux is to set the minimum quantum time to 10 milliseconds. That's in their best practices performance guide. So what do we want to look for when we are looking at CPU utilization? And I like to flippantly say percentage of what, right? And we're talking about CPUs. How do I consume 100% of a CPU? Is that like all the gigahertz? Is that all the cores, right? All the registers? What am I actually consuming 100% of? And I'm being flippant when I say that because it is a valuable metric. But the metric that I focus most on when I'm looking at high performance Linux-based systems is a thing called load average. What load average is the length of the run queue per core plus I/O weights. It used to just be length of the run queue. Now it's run queue and I/O weights. So if I have a 4-core system and I see a load average above 4, I know I'm in bad news, right? Because now I know that there's threads in each scheduler waiting to get access to the CPU and get going and do their work. So things are basically bottlenecking up. And so if it's a high performance system, I want to make sure that things are flowing through as fast as they can, right? And it could either be under CPU saturation or I/O saturation. Now, when it comes to CPU utilization, I like to say that spikes aren't bad, right? I don't care that my CPU went up to 100% or my load average went up a little bit for a small period of time, but did it come back down? And so for load average, which you can sample at any point in time, load average is calculated on 1 minute, 5 minute, and 15-minute weighted averages. So I can see, right, if I have a high load average in the last minute, all right, well, what's the 5-minute average? What's the 15-minute average? If I see it saturated at 15 minutes, I know I have a CPU issue. We also want to look at long waits, whether it's user waits or I/O waits or disk latency. These are all going to affect access to the CPU because we're going to transition into that sleeping state, right, because we're waiting on something that's external to the process itself. And we'll look at process states in a little bit when we get into the demos. So tools to use for process monitoring. Kind of the go-to task manager, I would say, like if you're a Windows person, you're used to using task manager, the go-to way to monitor system performance right now on your Linux system, or say point in time, not right now, like I'm going to go do it right now, is top and htop. So top is going to kind of give you that process listing of all of the critical performance data for individual processes. Htop is top's included with every Linux distribution. Htop is a third-party tool that's fantastic, great way to filter and sort and color code things. It's still all command line, it's ncurses based, but it's a great way to navigate through your process information. PS, which is short for process select, gives you all that perf data, but at a point in time snapshot. It's basically going to go sample it and write it to the screen at an individual point in time. Now let's say I got to dive a little deeper, right? I've already found the process that's causing me grief, right? I'm going to use these two tools to dive to the next level of detail, MPStat and PIDStat. What those are going to do are allow me to go a little bit deeper into what that process is doing. I can ask for an individual process if it's look at and sample its breakdown between kernel time and user time, right? I can ask it for a lot of other performance data that we're going to talk about in the other parts of today's session as well. So hold on to PIDStat. DStat is kind of the monitoring Swiss Army knife, where I can use that to query basically any system performance attribute and write it out to CSV. It's actually a very powerful tool that I use quite frequently. It samples every second by default, so I can get a good graphical representation of what system resource is being consumed. Basically, if you can think of the perf counter, it exists inside of DStat. Now, all of this data comes from something called procfs, right? In our Linux file system, there's a directory called /proc, which holds kind of the running state of the kernel, right? Basically, all the processes that are up and running, all of the kernel configuration, and all of the performance accounting data is inside of procfs. So that's where these tools get their data from. And sometimes these tools don't have the data that we need, and I'm going to show you a couple places to look for that very granular data that we might be interested in some severe performance situations. All right, so let's get into some demos. We're going to look at processes and threads, right, and how to identify those and differentiate between the two. We're going to look at load average under CPU saturation, and we're going to dig around in procfs a little bit together. So if you guys are having trouble seeing anything, do let me know. I'm on a new rig, and I'm using Bash on Windows to show these demonstrations today. So I'm logged into a SQL server. You can see my username at SQL and so I'm simply logged into the system. And the first thing I'm going to do is I'm going to change over into my demos directory. And in here, I have a script called mysqlcmd, which allows me to parameterize that with an arbitrary SQL file. Basically, I get around having to type my password because it's inside that shell script. And I can do things to just run enter and not have to fumble through typing my password for you guys during demos. So let's go ahead and open up a second terminal. So I have that running in this window. I'm switching over to this other window, same server, and I'm going to launch a tool called htop. Now let's walk through what's going on here. There's lots of data. We could spend a whole session just talking about this output right here. So I have 4 CPUs in my system. You can see right here, 1, 2, 3, 4. Green is good, right? Green is user time. That's the amount of time I'm spending in user space doing that work. Red is that process is going into the kernel and asking it to do something. The particular tables that we have today, I have memory constricted to about 8 gigs, and the table that I'm working with is about 10 gigs. So now you can see it's performing I/O, and it's constantly overflowing and having to go out the disk to get the data that it needs. So we have 8 gigs of system memory allocated, 12 gigs total approximately. And now let's go ahead and look at some task information. So tasks those are full processes. We have 54 of those, 195 threads, 62634 are running. I'm running checkdb, max.4, so I'm going to have 4 worker threads, and basically when it samples is when it's going to catch that. So now we can see my load average was creeping up. Normally if I'd reboot this system, this would be really low, a really low value. But you can see it's starting to creep up, 1.4, 1.5. This is now 0.53, and that's going to start creeping up 0.56 because I'm pushing a pretty hard workload that's saturating CPU. Now this list down here, we can use, oops, let me put the right window in focus. We can use the page up and page down, and let's go ahead and get this lined up just right for you guys to see. Let's go ahead and walk through this output here. So this output here from left to right, we have our process ID, right? So we see that parent-child relationship that I described in the presentation portion. So we have the 1136 process, which is basically the process that kind of bootstraps the system. And then we have 1553, which is the thing that's actually doing the work. So SQL Pals load it. It's doing the work, interacting with the Linux host extensions, and driving that workload. The user that's running this is MS SQL. The internal dynamic priority, 20, right? You can see that that hasn't changed. And we see niceness is 0, so I haven't changed the niceness of this process. Now to differentiate, we can see that these are definitely 2 different processes, right? Because they have different sizes of memory address spaces. So we see the base process, 194 megs, 193 megs. And then this process, 10.4. And then we can see these are all threads, right? Especially with the parent-child relationship of the thread underneath the 1553 process. So these all share the same memory space, which we'll talk a lot about in a second. So as we go through this list, we can see that the virtual memory size, we can see the resident set size. So that's the vert is the process address space. Res is the actual physical memory consumed. Shared memory, that's this SHR column. And then this is the actual process state right here. So if we look at this list, we'll probably catch one transitioning between, so this guy's consuming CPU, so there we see running, and it's probably going to transition back to sleeping in a second because it's going to go and wait on I/O. Now we have CPU percentage, percent memory consumed, the amount of time that this thread has spent active on the CPU. That's that time plus column, and then at the end there is the binary. So let's break out of here and switch over to root and go digging through proc. So I'm going to change directory into /proc, and we're going to do a quick directory listing here and see all the information that we have access to. So those numbers on the left are directories that represent currently running processes on our system. On the right, we have some files. We have a sys directory. Oops, sorry, team. We have a sys directory here that is our system configuration, and we have things like CPU info and mem info, things that represent the current running state of our system. So there's CPU info right there, and there's mem info right there. We're going to look at mem info very closely in a second. So let's go ahead and find the process ID of, so PID of SQL Server. 1555, excuse me, 1553, and 1136. We know we want the one with the higher value because that's the one that's actually doing some heavy lifting. And let's go ahead and change into that directory. So now we're in that directory. Let's do another directory listing. And this is the current running state of this process, right? And so if we look at this data, we have tons and tons of stuff to look at. And let's go ahead and do this. ls minus LA. We can see things that, some of these things are links back to other parts of the system. So we can see current working directory. Well, that's the current working directory of SQL Server, var opt MSSQL. The linked binary is opt MSSQL server. File descriptors, so any file descriptors that are opened by this process are actually going to be inside of that directory. We also have maps and mem, and there's also smaps, and those are different ways to represent the different types of memory that are allocated to this process. But the big bucket place that we're going to look at most frequently for the deeper dive information for an individual process is that file over there called status. And so we'll type more status and get a point-in-time view of that process. So here we see SQL Server is the name of the process. We have its UMask, which is kind of a way for it to assign permissions on newly created files for this particular process, the current running state, the thread group ID or the process ID, the parent process ID, and the user ID for the user running it. 997 translates into MSSQL. Now, there's a bucket load of memory information available to you here. So we have the peak memory utilization, the current memory utilization, the current peak physical memory utilization, the top one, this being virtual address space, the current resident set size, and we're going to talk a little bit about anonymous pages in a few seconds. And so this is some deep dive accounting data for this particular process. So let's break out of here. This is one thing I learned the other day. See how it spoils your terminal when you come in and out of files sometimes? So you can cheat, htop, break back out, and then you get a clean terminal again. Haven't figured that one out yet. So what happens when you use beta software, right? But it's fantastic, this Windows on Linux thing, or Windows services for Linux thing. All right, so let's move into memory and pages. And I just want to recap that we covered processes and threads. We looked at load average under CPU saturation, and we dove around inside of ProcFS a little bit. So now let's get into memory and pages. So memory layout and architecture for Linux. It uses a virtual memory architecture, right? What that means is each and every process that's executing in Linux thinks it has full access to all of the memory in the world. Basically, I think it's like 192 terabytes is the maximum. Is it terabytes or gigabytes? I forget. Probably terabytes. It thinks it has access to that entire address space. And now it's the function of the operating system to take that virtual address space and map that back into the actual physical pages. Now, this is interesting, right? How do we allocate pages, physical pages, right? The operating system has to do that work. And we'll talk about that in a second. The allocations to those threads are NUMA aware. So we will pull pages from what are called free lists on each node, right? So we do have that concept inside of Linux. When we're looking at pages, right, that's the unit of allocation at the physical layer and the virtual layer. You're going to look at something called an anonymous page. And it doesn't mean like it doesn't know about that page. What that means is that page was allocated by a user space allocator. And in the case of SQL Server on Linux, that's an allocator called JEmalloc. And that's going to be the thing that asks the kernel, hey, I need a page. And it's going to be the one that tracks that information. So it's an anonymous page. When you were looking at that accounting data in meminfo, that's what you want to look at. So demand paging. So how do we know when a page is in physical memory or in virtual memory? And let me say that more accurately. When I'm a process and I go access a virtual memory space, right, that page needs to be there physically, right? And the operating system has to manage the translation under the hood. If I go access a page and it's not there, and it's a new page, and I go and I need to allocate a page to it, that's called a minor fault, right? I'm simply going to allocate the page under the hood and make sure that that page is there physically for the virtual memory access that I just went after. If that page that backed that virtual memory space, the physical page, was the contents of that page were swapped out the disk, I'm going to have to go get a new page, copy the contents of that page from disk back over to physical memory, and then access that page. And that's called a major page fault, or a swap in. And this is bad news because you have to wait for that disk transaction, right? So you have to ask yourself, why would that page get swapped out? Well, there's two reasons why a page would get swapped out. First off is allocation, but the second is under time and pressure, right? Linux will go through and scan the working sets of processes and find pages that haven't been used in a long time. It'll swap them out and take those pages and put them on the free list for someone else to use, right? It makes sense. If you're not doing anything, I'm going to have it ready for someone else so they don't have to wait a long time for a memory allocation. We can also swap out physical pages under memory pressure, right? If I have two processes competing for memory, well, the operating system is going to say, well, you haven't used that page in a long time. Now I'm going to take that from you, cause you to swap out, and give your physical page to somebody else, right? Because that's a finite resource on our system. And if you start doing that, you're in bad news, right? Because you're waiting on disk I/O, right? And that can take a long period of time. And we'll talk a lot about that in a second when we get into the demonstration and how SQL Server reacts to memory pressure. There's also a concept called a file system cache in Linux. Any leftover memory, so it's kind of similar to the buffer pool in a sense, any leftover memory available on our system will be given to the file system as to what's called a file system cache. So it'll cache metadata and file data in memory such that it doesn't have to go out the disk when it has to access that information again. And it really increases the interactivity of the system, right? And we're taking that leftover memory and using it to cache that file system data. Now there's a way that we can tune how much memory, or let's say how much memory, we can tune how fast the operating system will tip over that buffer pool cache, file system cache, and give it to user space processes. And that concept is called swappiness, right? If I adjust the swappiness of the system, it'll tip over that file system cache faster, give those pages to user space processes. And that value is suggested by the product team to go from the default value of 30 to 10, right? Because chances are we're not really worried about the interactivity of our system, and that's the primary benefit of the file system cache is the interactivity. We really care about giving as much memory to SQL Server so that it can do its database engine job as fast as it can. So what do we want to look for when we are looking at memory? We want to look at high consumers of space, both physical and virtual. And if there is a disconnect between the two, if I have a large virtual allocation and a small physical allocation, I want to understand why. Did it page out for time? Did it page out for pressure? Am I swapping right now? Right? Those are the questions that I need to answer very quickly. We also need to look out for any external memory pressure on SQL Server. SQL Server on Linux doesn't have a resource monitor yet, as far as I understand. That it might be coming, might not. There's a conversation on Twitter I had with a person on the product team a couple months ago about this. Any external memory pressure on SQL Server is bad news because in Windows, we have resource monitor. The operating system signals to SQL Server and says, SQL Server, dump your caches. I need your memory more than you do. That concept doesn't exist inside of Linux. So what will happen is Linux will look at the process address space and just equal opportunity swap out the oldest pages, regardless of what they are. And it could be your plan cache. They could be your buffer pool, right? Those pages are now on disk, which means if I go do select star from table A and a large portion of my process address space is on disk, I'm actually going to have to go get those pages from disk. What's even crazier is if I go look at the DMV data for that query, it's going to think it pulled it from the buffer pool, right? Because it didn't, SQL Server hit in the buffer pool, the underlying paging subsystem put the pages where they needed to be, but it was an actual disk transaction, right? And so that can really skew your performance data and your observability to be able to see what's going on. And we certainly want to look out for excessive swapping. If swapping is going on a relational system or really a relational database system or really any system, you're probably suffering some pretty severe performance side effects. So let's look at some tools for monitoring. We know about procfs now, right? So we're going to look at procmeminfo, and we're going to look at that together here in a few seconds. In the last demonstration, we looked at status. And that was a per process memory allocations. We were looking at each of those buckets. Meminfo is going to give us kind of a global view across the system. We're going to use free. Free is going to tell us the total system memory. It's going to tell us allocate it. It's going to tell us free, and it's also going to tell us the size of the file system cache. Top and HTOP, there's kind of those task manager views of the world. We looked at resident set size over there a few minutes ago. We also looked at the virtual address space for an individual process as well. PS has this data, right? Another way to get that information out for our process selection. And VMstat and PIDstat are two very valuable tools for memory monitoring. VMstat is going to tell you if your system is swapping. It's going to tell you blocks in, blocks out, swaps in, swaps out, size of your page file, and things like that. So a very valuable tool there. PIDstat will help you identify which process is paging. And so we can run PIDstat -R, and it'll tell you the amount of swapping major and minor faults for an individual process. And it's a very valuable tool to really dig into what's going on inside our process when it's paging. So let's get into some demos. We're going to look at the memory layout for our system. We're going to isolate a memory hog, which we kind of already did using HTOP. We're going to apply a significant amount of external memory pressure to SQL Server and cause it to swap out. And so this will be a pretty fun demo. So let's go ahead and pop into that. All right. So very first off, our memory topology, free minus M. So I have about 12 gigs on my system. 8 gigs used, 3 gigs of free, and 196 megs dedicated to the buffer, the file system cache, and a remaining 3,030 available. If I do ls-r on my root directory, I want to push up that file system cache. So if you are light sensitive, avert your eyes for a second, because this is going to throw out a bunch of stuff to the screen. So basically what I just did is I'm dumping every directory contents to the screen by doing ls-r. Now it's going to go and it's going to have read all of that directory entry data from the file system. And now you can see my file system cache shot up to nearly 500 megs. So it's using that memory to support interactivity in the operating system. All right, so let's get into our next demo and look at more proc meminfo this time. We looked at status a second ago. Let's look at meminfo now. So this is system-wide, right? And there's tons of different ways to represent memory in our system. We see total memory up here, free memory, available memory, cached memory, active, inactive. Here's our active anonymous, bunch of stuff going on inside of here. So if you really need to dig into particular types of allocations for your system, this is where you're going to look for that data. Oh, let me go ahead and clean up that spoil terminal. There we go. All right, with that, I think I still have my workload running. Yeah, I totally left check to be running for like the last 20 minutes. These noise canceling headphones are keeping me from hearing my CPU fans, which are screaming right now. So let's go, and I'm going to background that, let that execute. I wrote a program called memtest. What memtest does is it's going to allocate the amount of memory that I pass as a parameter contiguously. So I'm going to allocate 7,000 megabytes of memory in the system. Now we know that I have about 11 gigs in my system, and the max mem for SQL Server is set at about 8 gigs. And so let's go ahead and run this. So what's happening now under the hood is it's allocating that memory. And it's going to take a second to allocate 7 gigs of memory, especially with the fact that I'm running CheckDB concurrently at the same time. So let's open up HTOP and look at what's happening. I have bucket loads of CPU utilization, and it's all red. What's happening here is the kernel is working really hard to allocate memory to that process, right? And so that's what all the red is all the allocations that it needs to do to support that new process that I'm creating that's simply going to allocate 7 gigs of memory, and then once it's allocated, it's going to continuously read it over and over again. Let me do one thing real fast. I'm going to go ahead and foreground CheckDB and kill that. I want to show you guys something. So with that running, right? So memtest is going to get all the memory that it needs. And so we can see my memory is way up high now. It was floating around 9 gigs a second ago. I'm pretty much at capacity, 11.4 of 11.6 gigabytes. I didn't pick that value 7,000 arbitrarily. I really want to get really close to the edge of the amount of swap on my system, right? So you can see I'm right at about 5 gigs and 5.87 gigabytes total that's available in my memory. If I allocated 8,000, one of my processes would get killed by the out-of-memory killer, and it would kill that process so that another process could live. That would be bad news. So I chose that so that nobody gets killed. Now let's go down here. Let's look at the resident set size of SQL Server. So the resident set size of SQL Server is the amount of memory that's in physical memory, right? So stuff that's on actual memory. This prior to this was about 8,000 megabytes. So 4 gigs of the process address space for SQL Server is now on disk, right? This is bad news because I have no idea what pages have been paged out, what memory pages have been paged out. And SQL Server doesn't know either, right? If I do a select star, those pages are going to have to get pulled back in, and I'm not going to know why my query is immediately slow. So while this is up and running, let's go ahead and look at PID. I don't need PID of again. I know it's going to be proc. Is it 1553? More status. So now I can go in here and I can see my total address space, actually it is right here, VM size, my total address space and how much of that is swapped. So right now 4 gigs of my total address space is on disk in my swap file. So it's going to break out of here and see where we are. All right, so that's up and running. Let's background that. And I'm going to start CheckDB running concurrently. And I'm going to immediately background that. So with that running, let's go ahead and check VMstat. So VMstat, I just took one sample and I want to walk through that data. If I can parameterize VMstat with 1 and take an intervaled sample. So here we can see the total amount of data in the swap, how much is free in my swap file, file system cache, swap in, swap out, block, so that's memory, block in, block out, that's disk. And then we can see I have context switches and then user mode, system mode, idle, waits, and stolen CPU time. So this is a good way for me to see what's going on in my system. If I run this over an interval, we can start seeing some big numbers in kilobytes here, right? This is lots and lots of data churning through swap. I'm basically, as I'm reading data in for CheckDB, other processes fighting to allocate memory and read it as well. So basically we're disk crashing here and everybody is sad. If I want to find out who, I type PIDstat. I try to type PIDstat -R, and I can get a sample of who's swapping. So here we can see in this output here, if we go scroll to the top, look at the column data, we can see that it's user ID, process ID, minor faults, major faults, virtual address space, resident set size. And if I look through this list, we can see certainly SQL Server has lots of minor faults, lots of major faults, and is definitely swapping significantly. So that's the way how we can identify who. We use VMstat to see if we're swapping, PIDstat to see who's swapping. So before my system totally freaks out, let me kill some of these guys. And let's do cool. All right. Good. So let's get back into the presentation because we have to wrap up soon. So let's go ahead and look at disks and file systems. So for file systems, if you just throw the DVD in and you install CentOS or RHEL, you're going to get XFS. That's the default file system on that distribution. It's my preferred distribution because of history, really. SQL Server on Linux also supports ext4 as well. So I really don't have any guidance to give you on which one to choose. Figure out which one works best for you. Block size. From what I understand now, block size really has a nominal impact on the performance on Linux systems on a relational database engine. The block size for these file systems by default is 4K. My advice to you is talk to your storage vendor because chances are they might have some suggestions to you on which block size to use. The product team gives us this optimization for our file system. They want us to turn off this thing called access times with the mount time option, no A time. In each file on a Linux system, there's a structure header. There's just a header that accounts for every time that something happens to the process. And one of those things that it accounts for is access time. Basically, anytime someone came along and touched the file. If I have a big giant file with a bunch of concurrent threads running in it, you can see how that would bottleneck trying to update that piece of information in the file header. And so that's a good way to eke out a couple percentage points of performance. When we're talking about disk performance, here's what I want to look for. Basically, am I overrunning my disks, right? Am I saturating my disk or my I/O subsystems? Am I doing it over long periods of time, right? I can saturate my disks for a little bit, right? Just like CPU, I want it to work, right? But I want to make sure that I'm not saturating it over time, and that's where baselining comes in. I need to understand what's normal. We also need to prevent swapping, right? Because if we're burning a bunch of memory and swapping out the disk, a regular I/O, and now that memory paging I/O is going to cause resource contention on my physical disks, right? So that can put us in a bad state. So the tools that we want to use for disk monitoring on our system, these are kind of the big bucket tools that I use almost daily. So IOstat, right? That's kind of the go-to place. We're going to go through all of the output on that in a second here. IOtop is going to kind of help us find out who's consuming a lot of IO. PIDstat can help us identify, again, who's consuming a bunch of IO. And then DStat, that monitoring Swiss Army knife that can answer a lot of questions about disk data. So let's go ahead and get into another demo and look at how we can identify who a high I/O process is. And then we're also going to look at some DMV data and see if virtual file stats shows us what we expect it to show us.
All right, you're at the 10-minute mark, Anthony.
All right, let me have more coffee then. I have to have a little issue here. Let's see, kill 2, 1, 2, 3, 4. Yes. Oh boy, you guys didn't see this. Oh boy, a little worried about that. All right, so let's get into the demo and run CheckDB again. There's CheckDB. I want to switch screens and look at IOtop. And IOtop should show me a bunch of IO being driven by SQL Server. And I'm running CheckDB. And so at the top here, I can see I'm burning about 500 megs a second in read IO. And I can see that across the threads, who's consuming that IO. Over here, that binary is SQL Server, right? It's doing that work. It's kind of be expected with CheckDB running. So let's go ahead and break out of here. We can also use another command. We said PIDstat -D. We can see again in the column data from PIDstat, we're going to have different output this time. This is going to be kilobytes read, kilobytes written per second. If we scroll down in this output, we can see SQL Server is definitely reading a bunch of data. Now let's go ahead and look at another tool, IOstat -dx. So IOstat -dx gives us kind of I think the core information is DBAs that we're interested in. It does it per device and also device mapper, which a device mapper is a way to represent a Linux logical volume. So our read requests merged per second, write requests merged per second. What Linux will do is we'll take physically adjacent IOs, merge them into a single IO, and then dispatch to physical IO, which makes sense, right? Because especially in the days of spinning disks, I want those things that are physically adjacent to be dispatched to the disk. The actual number of reads and writes per second in the number of transactions, right? And then the volume of the data that I'm reading, right, in kilobytes per second. So I'm moving a pretty good chunk of data, nearly 460 megabytes per second on the read. As DBAs, we care about average request size, right? That's the size of my IO. So that's a big deal to know that we're burning a bunch of IO. We're nearly at 1 megabyte on that drive right there. Average request size, so any queuing, is there anything in line waiting to get access to the disk? Await, this is the amount of latency from the point of the system call that dispatched the IO out to the drive to retrieve the data and it complete it. So we're looking at about a millisecond right there for that information. We can differentiate between read and write. And then there's this concept of service time. Service time is from the device driver down, right? So it's measuring latency at a different layer. Service time is no longer considered accurate and will be removed from this tool. So basically write that off as no longer accurate. And we can see percent utilization on the disk right there. So this is some core valuable information, right? Because if I look at the size and the amount of time I'm spending, and how much data I'm moving, I can start to figure out the patterns that are significant to my workload. Now with that, let's go open up VS Code. I still haven't switched over to Ops Studio yet for this demo, but I will, trust me. Let's go ahead and scroll down. I'm going to make all of this code available to you guys, and I'm going to run a query that we probably all have from our friend Jimmy May that tells us our disk latency. So I'm going to go ahead and highlight that code and run this. Format selection, execute query. And we can see my read latency is about 8 milliseconds. And so we did a lot of nasty stuff since I brought this instance up. And mostly I did read IOs. And so we can see that we're getting some good accurate information coming out of our DMOS file virtual stats. All right, so let's kill that and get back into our presentation and talk about some monitoring tools. So monitoring tools. Everything we've talked about so far has been point in time, right? Like I'm looking at what's going on right now. I need to be able to baseline that data, and I want to be able to answer that question of what happened when, right? And what's normal and what's not normal. And so these are kind of the go-to tools out of the box, right? There's like cool third-party software packages and things like that. But out of the box, these are the things that you can use. SAR, which is short for the System Activity Reporter, will go through and periodically sample a lot of the data that we looked at today, store it in a binary file, and you can go back and say, I want perf data between time X and time Y. What perf data do you want? Well, I can get CPU, memory, disk, network, all of those things that we've been looking at. DStat can write to CSV, which allows me to do really good stuff with benchmarking, right? If I want to really zoom in on an individual attribute, I can use DStat to help me measure that at a very granular frequency as well, because we can adjust the sample interval on DStat. So tools for monitoring SQL Server. Well, guess what? We still have DMVs, which I just showed you one, and we also have extended events, right? Because of SQL OS. And so those skills that you have to troubleshoot your performance inside of SQL Server really translate well over to Linux. But now we kind of know the other piece of the puzzle when we're looking at the system level stuff that's occurring inside of Linux. Now, new tools available for SQL Server on Linux, right? There's new stuff. So over the summer, there was a collection of DMVs that made it into one of the release candidates, and those vaporized. I'm assuming there must have been an issue. But those were exposing some pretty cool information, and I hope those things come back soon, right, with regards to process information and resource consumption inside of Linux. And you can see, right, in /proc, that data is there for the getting. So we just have to build those bridges to get that data into SQL Server. I'm sure the product team is shaking their head at me right now. PSS Diag, right? So from the support team, they implemented a version of PSS Diag for Linux, which is available there. A DBFS. So we learned about ProcFS today. Well, DBFS uses that same paradigm and exposes DMVs into your file system. So you can have /DBFS, and inside of there, you'll see all of the DMVs available for your version of SQL Server on Linux. So that's a GitHub project, completely open source, implemented in C++. Go ahead and work on that and contribute some code there. I have some demos at my blog post there for you guys to look at. And the CAT team did some great work with Grafana. So they were doing a lot of performance testing in their labs, and they used these tools to build some really cool visualizations of perf data. Some great stuff in there. So don't just listen to me, right? Microsoft actually in PSS Diag is using the same tools that we talked about all day today. MPStat, PIDStat, IOStat, IOTop, Free, and SAR. These are the things, right, the building blocks of their own troubleshooting methodologies implemented in PSS Diag. So DMV data and also system log information coming off of the operating system is what's being collected by PSS Diag. So cool stuff there. So let's go ahead and review. We kind of went through a lot of stuff in a short amount of time. We talked about the Linux system architecture, right, and system calls and how that interacts with the hardware. We looked at the SQL Server on Linux architecture and how that bolts on to Linux with the host extensions and how those interact with the operating environment. Then we marched through the critical system resources, CPU, memory, and disk, and we looked at tools along the way to help us really sift out what's going on, right? Load average on CPU. We looked at swap in and swap out for memory, right? And where to look at for those critical things, how much is being allocated, what types of pages are being allocated. And disks, we focused on latency, I/O size, queues, bandwidth, right? Those key metrics that we care about for disks, right? Then we zoomed out a little bit and looked at some monitoring tools that are available to give us the system-wide information, things like SAR, DStat, and the tools that are available from Grafana and PSS Diag. So I have lots of blog posts about lots of these topics. So here's some more information about that. I have several Pluralsight courses that go into much more detail about all these topics. So if you want free access to those, go ahead and hit me up. Talk a lot about some advanced performance topics, basic installation and management for SQL Server and Linux is all covered in these various courses. Now, I didn't make a lot of this stuff up. I got a lot of resources for you guys. These are the references that I used to build this deck. Microsoft's documentation is fantastic, right? Check out that Linux best practices document at the very top there. If you really want to get into some nuts and bolts stuff, the third link, that performance tuning guide from Red Hat, is fantastic. They will tell you what to change, what that change actually does, how that resource is consumed, and maybe an expected results. Really good internal stuff there. If you'd like to burn your brain with fonts and source code, go to kernel.org. And that will tell you a lot of what's going on under the hood. This deck actually has a lot of hidden slides. It's the deck that I used at Past Summit this year, so I had a lot longer of a window. And the hidden slides are included with the deck that I'm going to upload. So basically for each system resource, there's either 2 or 3 additional slides that go a lot deeper into allocations for memory, CPU scheduling, and disk I/O. There's some really cool stuff happening with how disk I/O is occurring. So check out that last link for some deeper dive information in there, and my deck will have a little bit more information about how I/O occurs in SQL Pal. So while we have some time left, I think we're going to go for a few more minutes. Is there any questions?
Just 2 right now. Are Microsoft Linux binaries digitally signed when distributed by Microsoft to the different distros?
I do not know. So that's
not a performance question, so.
Yeah.
But, I don't know either.
Yeah.
Maybe someone else will know and later on in the event. And then a comment/question when you were talking about disk and memory, they said, interesting. I would say that SSD is the best option for Linux because of memory handling pressure would be greater to disk so that we don't have to do so much rigid memory analysis a lot of the time. Software, etc. changes give you more wiggle room, I think. Not as good as memory, but still.
So yeah, so I agree with that, right? But we're talking about the difference between microsecond latencies and nanosecond latencies, right? If I'm going directly to memory, that's in the single-digit nanoseconds. If I'm going out the disk, that's going to be in, the best right now is going to be single-digit microseconds, right? And another factor to include in that isn't just the physical access time, but the actual function transfers in the system calls that have to go and do that work. If that page is right there, ready to go, it's there, right? If I have to park my process on the waiting list, I have to go get the page, pull it into physical memory, get back into the runnable queue, and then get back onto the CPU. You can see why I'd want that page to be there in memory in a high-performance system, right?
Okay, next question. Top shows SQL using 200+% CPU. What does that mean relative to server CPUs?
It's all those jokes I made about percentage of what? No. Basically, I have 4 cores, and it'll add it up. You can get potentially 400% CPU utilization. So it's 100% per core, basically.
Okay, then somebody had a comment, good presentation. The recordings and slides will be available in about a week. The recording will be online. The slides will be available then as well. For that question. Next question, will DMV expose all IO, VM, stat, proc details?
So those, I'm vague. All right, those DMVs that got pulled out over the summer, the ones that I alluded to in that one slide, I vaguely remember those showing some process internal information. The long answer is that. The short answer is I don't know, right? They have to bring that stuff in, and it doesn't exist today. But I vaguely remember that existing back in the day. So hopefully that'll come back.
And final question, have you tried to implement Nagios to monitor performance on SQL Linux systems?
No, I have not. The one thing that I am interested in, that's a good question, is DStat. So DStat is extensible such that it can query other things, and there's modules, right? So like MySQL has a module to go and get additional performance data. So that would be an interesting one. but I could see, there are some native, I'm trying to remember, I did Nagio stuff like in the early 2000s. There was some SQL Server plugins that went directly into SQL Server, so that would certainly still persist because DMVs are DMVs. Then the Linux performance data would just be standard Linux monitoring, so you could certainly devise an effective monitoring solution using Nagios.
Yes, and I happen to know a Nagios person, and the person asking this question knows me. If you can email me, and I can probably give you some more information. And then the last comment is just thank you for the presentation.
Cool. Thank you, guys. Thank you, Tracy, for moderating. Thanks, Pass, for having me. This has been a great event. And good luck, Denzel. Sorry I ran over a little bit, but I appreciate it, sir.
All right. That will be the next session is Denzel doing customer experience stories. So everybody stay tuned for that next session or go join that next session. And please fill out the survey for Anthony and let him know how well he did. And if there's any comments that you have for him, thank you.
Cool. Thank you guys very much.